Hello everyone. Imagine running multiple applications at the very same time, from browser, coding, music and much more. Have you ever wondered how that happens without any lag? Basically, that happens because of concepts like CPU scheduling, synchronization and multithreading. So, today we present our project, Real-Time Multi-Threaded Application Simulator. I'm Pragati and along with my teammates Parul and Arnav, we have built this project to make operating system concepts more interactive and easier to understand. While studying operating systems, we realized that concepts like scheduling and thread executions are mostly theoretical and difficult to understand. Hence, we created a simulator that turns these concepts into a real-time visual experience. As we all can see, this is how the interface looks like. Let's have a quick demonstration to understand how our interface works. On the very left-hand side, we have the option to configure our simulator, in which the first option is to thread our model, which could be one-to-one, many-to-one or many-to-many. Let me just select one-to-one as of now. Then user can increase or decrease the number of user level threads. And as we can see, while we are increasing or decreasing these, the number of kernel level threads are also changing, depending upon the type of model we choose. Then we have the option to select the scheduling algorithm, which could be round robin, first come first serve, shortest of first, shortest remaining time first, and priority scheduling. In case of priority scheduling, we have provided with the options like if the lower number wins or the higher number wins. Let me just select round robin. Then we have the option to select time quantum. For now, I am going for 2 ticks at a time. Then we have the option to edit the configuration, where we can provide the arrival time and burst time. Let me quickly set the arrival and burst time for all these 3 processes. So I'm just keeping the arrival time as 0, 3, 4 and then 3, 4, 6. Yeah. Let's play this. User can also pause if required and reset too. This is how our entire simulation is working. How beautiful is that looking? Now we have the most important thing, which is the Gantt chart, which is visible in the middle, and also the queue status with the CPU utilization on the right hand side, as well as the thread status, which could be new, ready, running or terminated. Now to understand thread visualization and mapping, I'm handing it over to Parul.
Thank you, Pragati. Now I'll explain the thread visualization and system design part of our project. This module visually demonstrates how each thread behaves inside a system. Each thread is animated and transitions to different states such as new, ready, running, blocked and terminated. The grey ones represents the new state, which means that the thread has been created but has not been executed yet. If we play the simulator, here the green one represents the ready state, which means that the thread is ready and is waiting for the CPU for execution. Blue one represents the running state, which means that the thread is executing its instructions in the CPU. Next we have the terminated state, which means that the thread has completed its execution. We have also implemented various threading models such as one-to-one, many-to-one and many-to-many model, which illustrates how user level threads interact with are mapped with the kernel level threads. First one is the one-to-one model, where each user thread is mapped to a different kernel threads, which allows independent execution and parallelism. Next one is the many-to-one, where multiple user threads are mapped to a single kernel threads. So blocking even just one thread will block the entire process. And finally, we have many-to-many, where multiple user threads are mapped to multiple kernel threads, which provides both efficient concurrency and flexibility. This comparison helps the users clearly understand the strengths and limitations of each approach. Next important feature is the ready queue, which dynamically captures the sequence of threads waiting for the CPU allocation. In addition, the system also generates real-time logs capturing important events such as thread arrival, execution, preemption and completion. To enhance the analytical understanding, we have also included performance metrics such as the CPU utilization graph and thread space distribution charts, which makes the simulator not only visual but also data driven. Now, to explain how threads safely share the resources using synchronization, I'll hand it over to Arnav.
Thank you, Parul. Now I shall be explaining the thread synchronization and backend engine of our project, along with a quick demonstration. In real systems, multiple threads often try to access shared resources at the same time, which can lead to race conditions. To solve this, we implemented synchronization mechanisms such as Mutex, Semaphore, and Monitor. In our simulator, threads are visually shown competing, waiting, and executing inside the critical section along with real-time updates like semaphore values and waiting queues. Now let me walk you through the interface. On the left panel, we can select the synchronization mechanism and select spawn threads, where each thread represents an independent process accessing a shared resource. We can also control the simulation speed and use playback controls to start or pause execution. On the right panel, we can observe the internal state in real time, including the current lock or semaphore value, the live code being executed, and detailed event logs. In the center visualization, the simulation is divided into three parts: the intersection where threads request access, the critical section where only one thread executes at a time, and the exit section where the lock is released. Now, as we run the simulation and spawn multiple threads, you can see that only one thread enters the critical section while others wait. Once the thread is released, the next thread proceeds, clearly demonstrating how synchronization prevents race conditions. Behind the scenes, our simulator is powered by a tick-based engine that manages scheduling, thread transitions, and synchronization logic, along with centralized state management. Talking about the technology stack, we use React for building the user interface, JavaScript for core logic, Tailwind CSS for styling, libraries like Zustand and Recharts for state management and data visualization. In conclusion, our project successfully bridges the gap between theoretical concepts and practical understanding. It provides an interactive platform where users can actually see how threads are scheduled and synchronized in real time. For future improvements, we can add features like deadlock detection, multi-code simulation, and custom algorithm support. Thank you for watching.